Deep beneath the frozen wilderness of eastern Russia, a colossal slab of planetary rock is snapping like dry window glass. Every standard rule in modern textbook geology says this rock should be softer than warm butter. Yet needles in monitoring stations across 6 continents just jumped violently at the exact same fraction of a second. Something physically impossible is breaking inside the blistering heat of the deep earth, and the shock waves are still racing outward. If you love exploring the strange secrets hiding right beneath our feet without any fake hype or exaggerated drama, tap the subscribe button. We dive into real planetary mysteries every single week, and joining now ensures you will never miss a major discovery. To understand why seismologists around the world are staring at their computer screens in total disbelief, we have to look closely at a wild, remote corner of our planet. Far to the east of Moscow sits the Kamchatka Peninsula in the freezing waters of the Sea of Okhotsk. This untamed region is crowded with giant snow-capped volcanoes, towering mountain ranges, and rugged coastlines that face the open ocean. It sits directly on the Pacific Ring of Fire, a massive horseshoe-shaped path where the vast majority of our world's earthquakes and volcanic eruptions take place every single year. People who live along the Ring of Fire are completely accustomed to the ground shaking beneath their feet on a regular basis. In places like Japan, Alaska, Chile, Indonesia, and eastern Russia, minor tremors and rattling windows happen almost every single day. Most of these familiar events start very close to the surface, typically within the first 10 to 30 kilometers of the planet's cold, rigid outer crust. When the ground snaps up there, every scientist understands exactly why it happened, because cold rock is naturally stiff, brittle, and easy to crack when stressed. A magnitude 5.8 earthquake just registered across international monitoring networks, including the United States Geological Survey and the Russian Academy of Sciences. A magnitude 5.8 is a very serious event that packs enough raw kinetic energy to crack concrete highways, damage bridges, shake tall buildings, and wake millions of sleeping people. Yet the sheer size of the shaking was not what caused veteran earthquake researchers to drop their coffee cups in absolute astonishment. The real shockwave hit the scientific community when the automated computers calculated the origin point, which geologists call the hypocenter or the focal depth. The digital readout showed that this powerful rupture did not happen anywhere near the surface where humans build cities, roads, and houses. It triggered at a staggering depth of more than 600 kilometers below the crust, deep inside the mysterious transition zone of Earth's mantle. To picture that incredible distance, imagine stacking more than 60 Mount Everests upside down into the dark belly of the planet. If you were able to get into an ordinary car and drive down a straight highway at normal speed, it would take you 6 full hours of nonstop driving just to reach that depth. Down at that level, you're nowhere near the familiar world of soil, dirt, groundwater, mining shafts, or solid surface bedrock. For over a century, standard geology textbooks have taught students a very simple and logical rule about how our planet works from the inside out. As you travel deeper into the Earth, the weight of hundreds of miles of rock above creates crushing pressure, and the temperature climbs to extreme levels. By the time you reach 600 kilometers down, the heat easily exceeds 1,000 degrees Celsius, which is hotter than glowing red lava leaking out of an active Hawaiian volcano. Under that kind of blistering heat and suffocating weight, rock is not supposed to behave like a hard, brittle stone anymore. Scientists fully expected the rock to behave like soft plastic, thick, warm honey, or modeling clay left sitting under the blazing summer sun. When you squeeze warm clay in your hands, it slowly changes its shape and flows smoothly without making a sound or cracking apart. It bends, deforms, and stretches, but it never shatters like glass. Because soft clay cannot snap or break, scientists long believed that deep earthquakes were physically impossible under the known laws of physics. They assumed the rock down there would simply deform smoothly and absorb tectonic stresses in absolute silence over millions of years. Yet here is a magnitude 5.8 rupture tearing open a fault line hundreds of kilometers down, releasing violent shockwaves that roared straight through the heart of the planet. The gap between what our best scientific equations predict and what the planet actually did is dangerously wide. Have you ever felt a real earthquake shake the ground beneath your feet? Or does the idea of solid rock moving seem completely strange to you? Leave a quick comment below with your thoughts, and hit the like button if you want to support genuine, fact-based earth science. To see why this breakdown in scientific theory matters so much for our understanding of the planet, we have to look at the giant engine that drives the whole globe. Earth's outer surface is cracked into several large, rigid puzzle pieces called tectonic plates that float on top of the hotter, denser layers below. These plates move continuously at a very slow pace, traveling just a few centimeters every year, which is roughly the same speed that human fingernails grow. In some parts of the world, two plates pull away from each other and create brand new ocean floor from cooling lava. In other places, Like eastern Russia and the Kuril-Kamchatka Trench, a heavy oceanic plate collides head-on with a continental plate and gets forced downward into the fiery depths. Geologists call this massive process subduction, and the sinking piece of oceanic rock is known as a subducting slab. It is essentially a cold, ancient conveyor belt plunging down into a scorching planetary furnace. For decades, the common assumption among researchers was that this sinking slab would heat up very quickly as it sank into the mantle. Early calculations suggested that within a few million years, the cold oceanic rock would match the temperature of the surrounding mantle and turn completely soft. If the entire slab becomes soft, warm, and ductile, it should slide down effortlessly into the deep interior without causing any sudden violent breaks. What modern seismic sensors are detecting today tells an entirely different and far more dramatic story. Cold ocean rock holds onto its freezing temperatures for much longer than anyone thought possible during its multi-million-year descent. The central core of the sinking giant remains freezing cold and exceptionally stiff, even while its outer edges are being cooked by the intense mantle around it. It acts like a giant frozen icicle trapped inside a boiling pot of thick soup. This massive temperature difference creates wild, opposing stresses inside the descending slab as it travels through the Earth. The outside layer wants to flow and stretch like liquid glass, but the frozen interior refuses to bend and resists the movement. When the mechanical strain builds up past the ultimate breaking point, the cold core fractures with sudden, explosive violence. This sudden fracture sends out powerful vibrations called primary and secondary seismic waves that race outward at thousands of kilometers per hour. Pay close attention to this next detail because it reveals a hidden mechanical process that very few people outside specialized geology laboratories know about. It turns out that plain temperature is only half of the puzzle because the rocks themselves are undergoing a bizarre chemical identity crisis. Deep down in the mantle, the minerals that make up the rock are literally being crushed and reorganized into entirely new crystal structures. Under normal conditions near the surface, the upper mantle rock is primarily composed of a bright green mineral called olivine. When olivine gets dragged down past 400 kilometers by the sinking plate, the crushing pressure squeezes its atoms together into a much tighter form called wadslite. Push it down even further, past 520 kilometers, and it transforms again into an ultra-dense mineral known to scientists as ringwoodite. Geologists originally believed these mineral transformations happened slowly and smoothly, like an ice cube melting quietly in a glass of cool water. They thought the microscopic crystals changed their structure one by one over huge expanses of time, without disturbing the solid rock around them. If the transformation is slow, gradual, and calm, the descending slab should remain structurally stable throughout its long, dark journey. Laboratory experiments using advanced diamond anvil cells, which can squeeze microscopic samples with the force of an entire mountain range, revealed a startling secret. When cold olivine is pushed past its physical stability limit, the structural change does not happen smoothly or quietly at all. Instead, tiny pockets of the mineral transform all at once in a fraction of a millisecond, triggering a dangerous reaction known as transformational faulting. When the crystals suddenly pack together into a much smaller and denser space, microscopic pockets of rock collapse instantly under the load. This sudden collapse generates intense friction, heating the surrounding stone so quickly that it turns into a razor-thin layer of liquid melt. That tiny layer of molten rock acts like slick oil on a steep road, causing millions of tons of solid rock to slide catastrophically in an instant. What do you think is more powerful, the crushing weight of hundreds of miles of solid rock or the hidden atomic forces locked inside tiny crystals? Take a quick guess in the comments right now, and if you are enjoying this breakdown, take a second to hit subscribe. This brings us directly to another huge mystery that has kept researchers awake late into the night for decades. It is the presence of something that seems totally out of place in the deep, scorching interior of the Earth, liquid water. When most of us think of water on Earth, we picture blue oceans, rushing rivers, rain clouds, and vast polar ice sheets. We never imagine vast quantities of water surviving in a subterranean place hotter than a blast furnace under crushing weight. When oceanic plates sit at the bottom of the open sea for millions of years, cold seawater seeps deep into the cracks and reacts chemically with the rock. The water molecules become chemically locked inside the crystalline lattice of hydrated minerals like serpentine, chlorite, and talc. When the heavy plate begins its long dive into the subduction zone, it carries trillions of gallons of this trapped ocean water down into the mantle with it. Scientists used to believe that all of this trapped moisture was squeezed out near the top of the subduction zone, within the first 100 kilometers of depth. That released water lowers the melting point of nearby rocks and creates the buoyant magma that feeds surface volcanoes like Mount St. Helens or Russia's Kluchevskaya Sopka. By the time a slab reached the deep transition zone, scientists assumed it had been baked completely bone dry. Recent deep focus earthquake data and high-pressure laboratory tests have overturned that entire traditional assumption. Under specific cold conditions, certain water-rich minerals can survive the journey down to 660 kilometers without releasing their moisture early. When they finally reach their absolute thermal limit deep in the mantle, they suddenly release their chemically bound water in a violent burst of superheated fluid. This sudden release of trapped water deep inside the rock is known among geologists as dehydration embrittlement. The trapped water cannot escape easily because the surrounding rock is packed together under billions of tons of overlying weight. As the superheated fluid expands with tremendous force, it acts like a high-pressure hydraulic wedge, forcing open microscopic cracks and allowing massive slabs of rock to slip and slide instantly. Think about the sheer, unbelievable scale of what is happening under eastern Russia at this very moment. We have an ancient slab of the Pacific seafloor that plunged into total darkness millions of years ago, carrying the chemical memory of ancient oceans. Deep inside the planet, that slab is simultaneously transforming its internal minerals, releasing superheated water and snapping its frozen core apart. A magnitude 5.8 rupture at this extreme depth sends shockwaves straight through the core and mantle of the entire planetary body. Unlike shallow earthquakes that lose energy quickly as they travel across fractured surface terrain, deep earthquakes project their energy outward through dense, high-velocity mantle rock. The seismic waves travel with incredible physical efficiency, ringing the earth like a massive, solid brass bell. Notice how this changes the way we have to look at global seismic monitoring networks around the globe. When an earthquake happens near the surface, the shaking is violent and destructive, but it is concentrated in a relatively small area right around the epicenter. When a deep focus earthquake strikes at over 600 kilometers down, the surface shaking directly above it might feel surprisingly gentle, but the vibrations spread out across thousands of miles. Residents in coastal towns across the Sea of Okhotsk in northern Japan might only feel a slow rolling sway that lasts for several minutes without causing damage. Meanwhile, delicate scientific instruments on the opposite side of the planet, in places like Europe, Africa, and North America, record exceptionally clear and crisp wave patterns. The Earth's deep interior acts like a giant acoustic speaker, broadcasting the deep fracture to every single continent simultaneously. If you had the chance to safely ride an exploration submarine deep into the Earth's mantle, would you take the trip to see it with your own eyes? Let me know your answer in the comments below. And don't forget to give this video a thumbs up if you find deep Earth science exciting. Here is the critical part of the story that is making seismologists genuinely worried about what could happen in the coming years. Deep earthquakes do not exist in total isolation. They are mechanically connected to the massive tectonic machinery that controls our surface world. When a deep slab breaks or shifts suddenly, it changes the pull, tension, and stress along the entire length of the subducting plate. Imagine holding a long, heavy steel chain that hangs down into a deep well while someone suddenly pulls and jerks on the bottom end. If the bottom of the chain slips or drops downward, you will immediately feel that violent, sudden tug right in your hands at the surface. In geological terms, this pulling force is known as slab pull, and it is the single most powerful driving force behind all plate tectonics on our planet. When a magnitude 5.8 event ruptures at 600 kilometers, it redistributes the internal stress along hundreds of kilometers of the descending slab. That sudden shift in stress can slowly travel back up the plate over weeks, months, or years, loading extra mechanical pressure onto shallow fault zones. Those shallow fault zones are the exact places where devastating, tsunami-generating megathrust earthquakes are born. History shows us that deep earthquakes in this specific Russian subduction zone have often been followed by massive, historic geological unrest. In May 2013, the Sea of Okhotsk experienced an enormous magnitude 8.3 deep focus earthquake at a depth of over 600 kilometers. It was so powerful that people felt light swing as far away as Moscow, which is more than 6,000 kilometers across the Eurasian continent. That historic 2013 event proved beyond any doubt that deep mantle rocks can support massive, highly complex ruptures that break across hundreds of square kilometers of fault area. It completely shattered the old scientific belief that deep quakes were limited to small, isolated, and harmless cracks. It proved that deep down, enormous structural failures can unleash energies that rival the largest and most destructive surface disasters in human history. What we are witnessing right now across eastern Russia is an ongoing sequence of deep mantle adjustments that scientists are tracking day and night. Automated supercomputers at global seismic centers are running continuous simulations to calculate where that newly released stress is migrating through the crust and mantle. Every deep jolt acts like a hidden physical nudge against the locked, shallow faults sitting right next to coastal populations. There is another fascinating aspect to these deep events that connects directly to the birth, history, and long-term evolution of our planet. Scientists use the seismic waves from these deep earthquakes like a giant medical ultrasound machine to take detailed pictures of Earth's unseen interior. By measuring how fast the waves travel through different internal layers, geophysicists can create three-dimensional maps of the deep mantle. These maps have revealed something truly breathtaking resting quietly at the bottom of the mantle transition zone. Beneath Russia, China, and Eastern Asia, there is a giant graveyard of ancient tectonic plates that have piled up over hundreds of millions of years. These old, sunken slabs do not just melt away quickly, they stack on top of each other, creating vast underground continents of cold, dense rock. This subterranean slab graveyard acts as a massive thermal barrier that interferes with the normal circulation of Earth's internal heat. Heat, trying to rise from the superhot liquid iron outer core, gets blocked and redirected by these massive piles of cold, sunken slabs. This dynamic can cause giant plumes of hot rock to form along the edges, slowly rising toward the crust over tens of millions of years to create massive volcanic hotspots. Did you know that pieces of ancient ocean floors from the time when dinosaurs walked the Earth are still sinking through the mantle right now? Tell me if that fact surprises you in the comments below, and be sure to subscribe so you never miss another deep dive into Earth's greatest puzzles. Scientists are now actively asking whether these frequent deep ruptures are signaling a major phase change in the subduction system beneath the Northwest Pacific. The Pacific Plate is currently moving faster than almost any other tectonic plate on the globe, plunging into the mantle at up to 8 centimeters per year. That relentless speed forces enormous volumes of cold, mineral-rich material into the transition zone at an extraordinarily rapid pace. When you push cold, waterlogged material into a hot, high-pressure zone too quickly, the planetary system cannot reach a calm thermal balance. The rocks are subjected to extreme temperature differences and rapid mineral phase changes long before they have time to warm up and settle. The result is an unstable, highly dynamic environment where internal stresses build up to dangerous levels much faster than previously estimated. This means that our standard seismic risk models might be missing a critical, foundational part of the whole equation. Most earthquake hazard assessments focus almost entirely on the shallow faults that we can easily see and map on the surface using satellites and ground surveys. They calculate earthquake risks based on how much the surface rocks are bending and how many years have passed since the last major surface break. If deep focus earthquakes are constantly shifting the stress loads from underneath, the surface faults might reach their breaking points much faster than expected. A shallow fault that looked calm, quiet, and locked could suddenly receive a massive surge of transferred stress from a deep rupture 600 kilometers below. It is like trying to predict when a building will collapse by only looking at the roof tiles, while ignoring the shifting concrete foundation deep in the basement. This ongoing seismic activity in Russia is forcing geophysicists to rethink the fundamental laws of how solid matter behaves under extreme physical limits. The fact that rock can break with explosive, high-speed velocity under pressures exceeding 20 gigapascals challenges our modern understanding of solid-state physics. It shows that nature still holds profound secrets that our most advanced high-tech laboratories cannot easily duplicate or explain. Researchers from universities and research institutions around the world are rushing to deploy new broadband seismometers across the Arctic, Siberia, and the Pacific Rim. They want to capture every single tiny aftershock and microtremor echoing from this deep event. By analyzing the high-frequency vibrations in the seismic signals, they hope to determine whether the rupture was caused by mineral phase changes, fluid explosions, or runaway frictional melting. Every new piece of seismic data brings us one step closer to solving the century-old mystery of the deep Earth. It is a powerful reminder that the ground beneath our feet is not an inert, unchanging ball of dead stone floating in space. It is a living, churning, dynamic planetary heat engine that is constantly recycling its own surface, transforming its chemistry, and shaping the destiny of the continents above. When we zoom out and look at our place on this planet, it gives us a deep sense of humility and wonder about the world we inhabit. We live our daily lives on a thin, delicate skin of cool rock that floats on top of an enormous churning world of extreme heat and pressure. Everything we build, every city we love, and every road we travel depends entirely on the restless stability of the deep interior miles below us. To truly appreciate the incredible power of these deep mantle events, we must also examine the sheer amount of physical energy they produce. When a fault ruptures at the surface, a large portion of the energy is spent breaking apart weak, weathered rocks and creating surface rubble. But down at 600 kilometers, the surrounding rock is under such intense confining pressure that it takes an unfathomable amount of force to create a fracture. This means that a magnitude 5.8 earthquake at great depth is fundamentally different from a magnitude 5.8 near the surface. The stress drop, which is the amount of force suddenly released when the fault slips, is often vastly higher in deep focus events. The rock does not just slide gently, It snaps with extreme concentrated violence that sends exceptionally sharp, high-frequency energy pulses tearing through the planet's interior. As these high-energy waves travel upward, they encounter different layers of the mantle, including the upper mantle and the asthenosphere. The asthenosphere is a semi-fluid layer of partially molten rock that sits directly beneath the rigid tectonic plates. When seismic waves from a deep rupture pass through the asthenosphere, they can cause subtle, widespread disturbances in the slow-moving convection currents that circulate within it. These convection currents are the very circulatory system of our planet, moving heat from the deep interior toward the surface over millions of years. When a sudden deep rupture occurs, it creates a localized pulse of motion and heat that can disturb these slow convective flows. Over long periods, these small disturbances can influence how magma rises toward the surface beneath active volcanic arcs. Consider the Kamchatka Peninsula, which sits directly above this active subduction zone and hosts some of the most explosive volcanoes on Earth. Volcanoes like Klyuchevskaya, Sopka, Shiveluch, and Bezimiany are known for their frequent violent eruptions that send ash plumes miles into the atmosphere. The magma feeding these giant volcanoes is generated by the complex interaction of heat, water, and melting rock within the subduction zone below. When a deep earthquake releases fluids and alters the stress field hundreds of kilometers beneath a volcanic arc, it can change the pathways through which magma travels. While a deep rupture does not instantly trigger a volcanic eruption the next day, it can slowly alter the pressure inside deep magma reservoirs over subsequent years. Scientists are now using satellite radar to measure whether the ground around Kamchatka's volcanoes is swelling or sinking in response to these deep tectonic shifts. Do you think that deep earthquakes and volcanic eruptions are closely connected, or do you believe they operate as completely separate systems? Drop your thoughts in the comments section below, and remember to subscribe to the channel to keep up with the latest planetary updates. The technology we use to study these deep earthquakes has advanced dramatically over the last few decades, opening new windows into the abyss. In the early days of seismology, scientists relied on mechanical pens, drawing ink lines on paper drums to record ground motion. These early instruments could tell that an earthquake happened, but they could not provide the fine details needed to understand deep mantle physics. Today, global seismic networks use ultra-sensitive broadband seismometers that can detect ground movements smaller than the width of a single atom. These instruments are connected to satellite communication systems that transmit real-time data to supercomputing clusters located across the world. When a deep event occurs beneath the Sea of Okhotsk, scientists in Tokyo, London, and California receive the exact waveforms within seconds. Using advanced mathematical techniques like seismic tomography, supercomputers process these waveforms to construct high-resolution images of the subducting slab. It is very similar to how a computerized tomography scan, or CT scan, creates detailed cross-sectional images of the human body in a hospital. These seismic images allow researchers to see the exact shape, thickness, and angle of the sinking Pacific plate as it plunges into the mantle. What these high-resolution images show is that the subducting slab beneath Russia is not sinking in a simple, straight line. Instead, as it hits the boundary between the upper and lower mantle at 660 kilometers, the slab begins to bend, buckle, and fold like a crumpled rug. This boundary, known as the 660-kilometer discontinuity, acts like a semi-rigid floor that resists the slab's downward motion. As the cold slab crumples against this deep planetary floor, the internal mechanical stresses reach astronomical levels. The front end of the slab is essentially hitting a wall, while the heavy back end is still sinking rapidly from above. This collision creates a massive zone of intense compression where the rock is squeezed from multiple directions simultaneously, setting the stage for powerful, deep ruptures like the magnitude 5.8 event. If you find it amazing that we can use sound waves to image the inside of our planet thousands of miles down, let me know in the comments. Be sure to hit that like button to help more people discover the incredible science behind how our planet works. Another intriguing question that scientists are racing to answer is whether deep earthquakes could occur even deeper than 700 kilometers. For decades, global seismic catalogs have shown a complete and abrupt cutoff in earthquake activity below 700 kilometers depth. No matter how large the subducting slab is, earthquakes simply seem to stop happening once rock passes that mysterious depth line. The reason for this sharp cutoff lies in another massive mineral transformation that occurs at the top of the lower mantle. At 700 kilometers down, the mineral ringwoodite breaks down completely into two even denser minerals called bridgemanite and ferropericlase. Bridgemanite is by far the most abundant mineral on our planet, making up more than half of Earth's total volume. Under the immense pressures and temperatures of the lower mantle, bridgemanite and ferropericlase behave very differently from the minerals above them. They flow and deform much more easily under stress, preventing the rock from storing the elastic strain needed to produce a brittle fracture. Below 700 kilometers, the planetary rock becomes so ductile that it can no longer snap, bringing an end to the earthquake zone. Yet occasionally, ultra-sensitive seismic instruments detect faint, anomalous signals originating from depths of 750 or even 800 kilometers. These ultra-deep events are exceptionally rare and remain one of the most controversial topics in modern geophysics. If an earthquake can truly happen in the lower mantle, it would mean our understanding of mantle rheology and mineral physics is still incomplete. Every deep earthquake that occurs beneath Russia and the Northwest Pacific provides valuable clues that help solve this fundamental mystery. By carefully analyzing the exact depth and rupture mechanism of this magnitude 5.8 event, researchers are refining their models of where the brittle ductile transition truly lies. They are discovering that the boundary between rock that snaps and rock that flows is not a flat, simple line, but a complex, jagged landscape. This complex subterranean landscape is shaped by the temperature, water content, and age of the subducting oceanic crust. Older, colder oceanic plates, like the ancient Pacific plate beneath Russia, can carry brittle conditions much deeper into the mantle than younger, warmer plates. This explains why the Sea of Okhotsk and the Kamchatka subduction zone are home to some of the deepest and most powerful earthquakes ever recorded on Earth. Have you ever wondered what other hidden structures might be resting thousands of kilometers beneath our feet that we haven't discovered yet? Share your biggest questions about the deep Earth in the comments, and don't forget to subscribe to stay connected with our ongoing investigations. As we look to the future, understanding the deep connections between the mantle and the surface is becoming increasingly important for human society. Millions of people live along the coastlines of the Pacific Ring of Fire, building cities, ports, and critical infrastructure on active tectonic margins. Improving our ability to assess earthquake and tsunami hazards requires us to look beyond the surface and understand the whole planetary system. When deep focus earthquakes transfer stress back up toward the surface, they can potentially bring locked megathrust faults closer to failure. By incorporating deep mantle stress modeling into regional hazard maps, seismologists hope to develop better long-term forecasting tools. While we may never be able to predict the exact minute an earthquake will strike, understanding these deep stress transfers helps us identify which regions face heightened risk. The study of deep earthquakes also gives us profound insights into how other rocky planets in our solar system might function. Planets like Mars and Venus do not have active plate tectonics like Earth, but they still possess deep internal heat and mantle convection. By studying how rocks deform and fracture under extreme heat and pressure on Earth, planetary scientists can better interpret data from space missions like NASA's InSight lander on Mars. In many ways, the deep interior of our own planet is just as alien, mysterious, and difficult to explore as the surface of another world. We cannot send robotic rovers down to 600 kilometers, and no human drill has ever penetrated deeper than 12 kilometers into the crust. Seismic waves remain our only true probes, allowing us to listen to the faint whispers and violent snaps echoing from the deep darkness. The recent magnitude 5.8 earthquake beneath Russia is a vivid reminder that the Earth is an active, dynamic, and evolving world that continues to surprise us. Every time a deep fault snaps in the transition zone, it challenges our scientific theories, pushes the limits of our technology, and reminds us of the immense natural forces shaping our home. The story of what lies beneath our feet is still being written, one seismic wave at a time. If this deep Earth mystery gave you a whole new appreciation for the restless, powerful planet we live on, please hit that subscribe button right now. Turn on the notification bell so you are always the first to know whenever a major new scientific discovery breaks. What do you think is the most astonishing part about rocks breaking at 600 kilometers deep? Leave your thoughts in the comments below and share this video with a friend who loves space, science, and the great unexplained mysteries of our world. Thank you so much for watching, and stay curious until next time.